Welcome, and thank you for taking the time to join us today and for your interest in our continuing education course. My name is Tony Barnes, and I'm an engineer with Sightline Commercial. And today we'll be covering how demountable equipment can enhance the flexibility, safety, ADA compliance, and social distancing capacity inside of a venue. As an industry leader, it's our intention to assist you with the basics regarding the importance of these products in your design process, ensuring safety while maintaining design intent and aesthetics required for successful end results. Working together from concept to completion with the brightest and most experienced teams available in a collaborative effort is the key to any project success. So we'll touch on that a lot here. With all this in mind, let's begin by starting with defining the purpose and learning objectives of this course. So the purpose of today's presentation is to examine the use of demountable equipment, including platforms, stairs, ramps, railing, and seating, with a focus on application, patron safety, building code requirements, social distancing, and structural design in public spaces. All these items are critical to your design, and many of your choices will affect project budgets and the future use of the venue. As we progress through this material, we hope that the end result will give you a foundation to begin the design process of incorporating demountable equipment into your projects. At the end of today's program, you'll be able to identify applications for demountable platforms and equipment in public spaces, discuss the solutions for patron safety and current trends regarding patron experience and social distancing, apply 2018 IBC code criteria related to demountable platforms to the design of safe systems, identify structural design considerations for demountable equipment in specific field applications, and specify demountable equipment that is appropriate for the project goals around safety, budget, and venue flexibility. So now let's move into the application and the components. Demountable systems can be used for many purposes in any facility. However, we have two common ones that we'll talk about here. That's sport arenas and performing arts venues. They require maximum flexibility for a variety of events they host. So the first type of facility we'll explore is a typical sports arena or football stadium that you see here. As you look around the stadium, you see the areas where demountable equipment could be installed. Most of this equipment is built using standard demountable platforms in different applications, but you will also notice some semi-permanent and architectural applications for this type of equipment as well. In a stadium or arena, demountable platforms can be used to create ADA seating infills and ramps, flexible camera positions, VIP and loge box seating areas, event level seating sections, vomitory spanning sections, and concert performance staging, all using similar standard components to maximize the flexibility of the equipment being used. Other types of demountable equipment include field stairs and forkable seating systems typically found around the field level of a stadium. In a performing arts or theater setting, most demountable equipment is found on or near the actual stage area in the form of stage traps, orchestra pit fillers, stage extensions, and band or orchestra risers. ADA infill platforms, movable seating wagon systems, seating riser platforms, and lighting or sound mix positions are found away from the stage area. These venues need flexibility in the way that stage and audience areas are arranged related to how the space will be used. For example, different stage and audience configurations are needed for different types of performances, a play versus a musical performance, for example. Movable unitized sections with adjustable height settings provide all the flexibility you need. In some theaters, they may have a dozen or more setups, specific setups used for audience seating. Some additional applications where you can find demountable equipment would include pool covers, choir risers at worship facilities, and for various uses for corporate events. What is showcased here in the photo on the lower right is kind of an interesting application at a boat trade show where the flooring is actually raised up so that the patrons can get a better view inside the boats being showcased. Essentially, they create docks all around the trade show floor. How is that flexibility achieved? Now that you've seen some of the applications where we'd use the demountable equipment, let us talk about the components that make up these installations. We have platforms, supports, stair units, guardrails, equipment accessories, and ADA systems. Let's first talk about the most important building block of the demountable unit. That is a platform. It usually consists of a plywood deck with an aluminum skin backer. That aluminum skin provides a fire rating, a Class A fire rating for the entire platform. The platforms have a locking system to create a single monolithic surface. That's important both structurally and aesthetically, as well as just for serviceability, so you don't have tripping edges. We'll discuss that engineering part of it in later slides. They're typically engineered to adequately support the code required loads. You can get higher capacities by adding a beam in the field of the platform or multiple beams. The frame is also important. We use a lightweight frame that keeps them manageable because you have facility staff members, usually two of them, striking and setting up the equipment, so they need to be manageable. They're also very easy to customize for size and structural capacity. As noted previously, we use a plywood typically that's easy to cut and to cut the edge extrusions and form it around there, around the plywood edge. You can use almost any surface on top. Paint, carpet, hardwood, or tile can be applied to the plywood. Here's an ISO view showing a typical platform stack up, also showing the optional beam for increased capacity and the acoustical insulation for sound attenuation. For outdoor applications, we might use a polymer or fiberglass panel, aluminum plank, or a wood plastic composite decking material to provide more weather resistance. And you can see here also that there's a lot of different surfaces you can have on the plywood. Another one we use most commonly as a wear surface is just a polymer top layer laminated to the plywood. Here's an example of an aluminum plank that we talked about. It's slightly more expensive than the plywood, but it provides long-term, very long-term resistance to the weather. So now let's get into the different types of support systems. The support system for demountable platforms usually chosen based on its application and use. Typical options you will find include standard legging systems, bridging platform systems where the structure lies beneath every other platform, beam and column systems, typically used where the space underneath the platforms must be available, forkable systems, and rolling systems. Again, system selection should be based on multiple factors, including but not limited to use, storage, cost, and setup size. Successful project execution starts early in the project lifecycle. Contact the local demountable supplier. Discuss these factors with all project stakeholders. Now let's briefly discuss some of the most common support systems in a little bit more detail. So we talked about standard legs. These are by far the most common style support, offers the lowest cost up front, highest flexibility, and smallest storage footprint. Note you can see in the slide here that the legs are able to be stored inside the platform cavity, either loosely or in flashlight clips where the platforms are stacked on carts. Standard legs are offered in either fixed or adjustable height range, but require bracing once you reach heights in about excess of 30 inches in most applications. Note the photo in the slide here shows those diagonals. Standard legging is great for stadium overbuilds when you're spanning the platform over an existing concrete tiered bowl to create an ADA or camera platform around the concourse of a stadium. They also work great in theaters for flexible seating configurations below 30 inches in elevation for their ease of use and quick setup strike times. Of course, if you go above 30, that's possible. You just need more diagonals that cost a little bit more time. Let's talk about bridging systems. They're used frequently for larger setups, taller elevations, and faster strike and setup times. These types of systems bridge platforms from front to back, left to right, between the supporting frames, eliminating additional understructure and opening up space underneath the demountable equipment. You can either span obstacles or actually make corridors through there and gain access underneath the equipment. Because there's less legs dropping to the ground, time to level the system's also decreased. There's just less supports than the traditional leg system that we talked about in the previous slide. It can be a huge advantage to an installation team that has a large setup to do in a short transition period between events. Bridging supports are available in both lightweight aluminum and steel. 90% of them are probably made out of lightweight aluminum, just simply because of the reasons we talked about before. You need people on site to handle them easily. As you can see in this slide, carts can be designed to hold each style of the bridge support to conveniently assist with storage and transportation. We'll talk about carts here shortly. First, let's talk about the beam and column systems. They're used to span great distances, higher elevations, usually 9 or 10 feet, 8 to 10 feet really, when you need to have access underneath. It requires the most engineering assistance up front. It's usually highly custom, and there's usually longer spans to deal with. And to meet code, you need to talk about that stuff in a little bit more detail. It's not off-the-shelf engineering. Highly customizable, used for both demountable, semi-permanent, and permanent, even permanent solutions. You'll find this style of support typically around a vomitory area in an arena or in a stage trap of a theater where you need a lot of open space underneath, where you have people or equipment passing underneath or using that space. Then we have highly customizable, forkable seating systems. They're meant to yield additional seating capacity for venues without increasing setup difficulty. This product is designed to fit into tight venue-specific storage areas, but also achieves a sturdy and permanent quality that allows patrons to feel as though they are standing on solid ground. With towers that combine both bridging from left to right and front to back, this caster-mounted product is long-lasting and transportable. Optional accessories include step units, handrails, guardrails, field walls and padding, camera or video platforms, and you can attach them down to the structure with anchorage if you need to resist wind loads. Leveling feet ensure that that the rise of the product matches the adjacent concrete of the stadia, allowing the riser to adapt to any unique area or space or fit in pretty much seamlessly with the surrounding stadium. Typical forkable risers include an aluminum plank top surface and mounted seats. Forkable riser systems are typically compatible with any type of seating chosen for the venue, highly adaptable to match the look and feel of the space. This type of system requires the most upfront design and engineering system, as concepts like wind loading, dynamic loading, storage logistics, probably the most important concept to consider, need to be worked out well ahead of time with all the project stakeholders, especially the facility managers, to ensure that the project is costed correctly upfront. No details are missed that may derail a project or cause the system to be virtually useless or very, very expensive to use if you don't talk to the facility people early on, and that can last into the life cycle of the equipment. Okay, let's talk about accessories. They're typically attached to the aluminum frames of the platforms. You see this on the lower left-hand slide. The platform frames are extruded aluminum with grooves to accept the accessories. Here you can see that we have guardrail and drink rail. You could also have ornamental or architectural guardrails, or a drink rail for that matter. Here's a few of the ideas. Any design can be accommodated. Whatever's needed architecturally can be top mounted to or attached to the extrusions like we talked about in the previous slide. We have fixed and adjustable stair units. All of these adjustable and fixed units, with the exception of the one on the bottom right, are very much a standard product. The one on the bottom right is usually a custom product for a venue, a field stair unit to get down to field level for a venue or for a concert, for example. Closure panels and skirting, very common add-ons for demountable applications, cover support systems, and act as chair stops on seating risers. So let's talk a little bit more about the carts. You need a way to store and transport the equipment when it's not in use. So depending on the type of venue and storage space available, having the right style of transportation carts is just as important as any other aspect. You need to navigate the space, carry all the equipment needed. It's important to pre-plan the storage spaces out to make sure the equipment is being designed for the venue will ultimately fit into the storage space available. Each cart is designed specifically for high capacity, easy maneuverability, or for small overall storage footprint. Flatbed carts are great for higher capacity per cart needs, and small components like legs can be stored in cavities like we talked about in those flashlight clips between stacked platforms, so it's very efficient. Vertical style platform can be designed to fit through a platform cart can be designed to fit through a standard door, which may be important depending on the venue. It has varying capacities depending on the size of cart that can be maneuvered through the building. Stacking carts are great options, are really efficient when a forklift is available. You can cut the storage footprint in half by stacking these on one another. From there, you can see there are various cart designs for the different accessories and supports, all meant to store equipment as organized in an efficient manner. ADA needs. Wheelchair and equipment ramps can also be built from the demountable equipment fairly easily. We'll get into more detail how these actually meet and what ADA code has to say about these areas. Before we talk about some of those engineering items that we've sort of alluded to, let's talk about the project process. We have some understanding of the equipment. Now let's discuss how we incorporate it. So virtually all project cycles can be broken down into four main processes: planning, design, development, and deployment. Traditionally, the bulk of the planning and design phase is carried out by the architects and consultants specializing in conceptualizing design, creating the drawings and corresponding specs, and budgeting to ensure the overall project remains viable for the stakeholders. We're going to take a deeper dive into how incorporating a design assist approach into the planning and design phase facilitates successful projects, especially those containing custom aspects. So finding knowledgeable, reliable, and experienced partners is a cornerstone for any successful project, which we probably all understand. This slide identifies the 4 major roles of a demountable contractor during the project lifecycle. More complex or custom projects require partners take on an even greater responsibility to ensure the final product matches the design and fits within the planned budget. Therefore, the pre-construction phase is arguably the most important because in this phase, the most efficient design can be agreed upon according to the project design requirements and, very importantly, the budget demands. While some of these details can be determined later in the bidding process or even the execution phase, experience has shown that this increases the budget, opens the manufacturing and installation phase to a higher degree of risk for communication, potential pitfalls, usually in the form of change orders and things that the ownership and the general contractor don't like to see. So, in essence, a successful pre-construction phase leads to these other 3 execution phases being successful. Again, the key takeaway is that early collaboration with the design teams and a strong, experienced partner result in a more successful project economically and aesthetically, just illustrated in this slide. Typical project workflow is shown in the above chart, with the understanding that each project is unique and can progress differently. This is fairly typical in a general sense. Architects and consultants create the initial design and define the budget and scope of work considerations. That's given to a GC or construction manager to facilitate the bidding process. During the bidding process, the project team vets out and considers proposals of engineers, manufacturers, and installers to put together a package that hopefully ends in a result that meets both the vision, the architectural intent, the design intent, and fits within the planned budget. So we know that sometimes that doesn't work out as planned. The below chart illustrates the design assist approach. Especially useful for those custom applications. You involve the manufacturer early in the design budgeting process. Stakeholders gain deep insight into the variables that can affect budget, or you can make a design that fits within the budget. Potential risks incurred during production or installation caused by the unique design application can be addressed. Just to be clear, this process does not circumvent the standard bidding process. Although it's true that there are certain projects that are awarded directly, bidding remains a viable option for the design assist approach. It's just that you hopefully have a better design up front. You provide that 3D modeling, budgeting, etc. The manufacturing partner benefits by having a clear understanding of the scope and expectations, and they can manage their budget accordingly. Positive result of this approach is that you get a design, again, that is more in line with the budget and more in line with the aesthetic when it's all said and done. So let's talk now a little bit about the engineering. We'll talk about the code and the loading requirements in general. So I think that in many instances, knowledge of the technical details is left up to engineers, but in my experience as an engineer, all members of strong project teams are able to have some understanding of the technical requirements so that good early design decisions can be made. Costly changes don't occur later in the project lifecycle. We'll start by discussing the code requirements. As you're all aware, the primary purpose of codes is to provide the minimum requirements to adequately safeguard the health, safety, and welfare of building occupants. In this slide, you will see most of the code associations that are used to guide demountable system design. Primarily, and in most jurisdictions, the International Building Code is most widely referenced here in the United States, determines most aspects of design. Local codes either adopt the IBC outright or produce a document of their own, starting with the IBC as a basis. Generally, the code requirements for demountable systems are divided into 2 primary categories: geometric requirements related to egress and structural requirements. In addition, there are some requirements related to fire protection depending on the use of the system. We won't dig too much into that here. Demountable assemblies can be used for a wide variety of applications, so there's lots of code sections that need to be considered. Geometry of a system is primarily dictated by occupancy and the needs of those occupancies. Considerations such as sightlines and overall geometry are primarily determined by the design team. Well, building code requires various configurations of aisles, stairways, ramps, handrails, guards, and doors. Simply ensures that the users of that facility can safely move about and use the system. Those geometric requirements are primarily provided in Chapter 10 of IBC, means of egress, mostly mirrored in the ADA standards. You also might have some OSHA standards that need to be met for platforms and work platforms and ladders, for example, camera platforms. Those are similar to the IBC requirements, or they're unique and they're not items that are covered in IBC. Structural requirements, which we'll discuss in the coming slides, are primarily provided in Chapter 16 of IBC. Many of the material-specific design requirements are in other standards that are referenced by IBC, such as for steel and aluminum. NFPA for fire protection and IBC should be referenced for the fire resistance requirements. Again, suppliers have a wide variety of solutions using different materials to achieve the necessary levels of protection as required by project-specific construction types. We won't get into too much more detail for fire protection. Note that in all cases, local jurisdictional codes should be consulted. Again, most have adopted IBC and related codes, but many jurisdictions have a few amendments here and there that vary from the IBC language. Let's talk about the loading requirements. Generally, as you're all somewhat familiar with, loading requirements are the forces that are required to be applied to structures. They come from gravity loads, dead loads or self-weight, human activity that we call live loads in the environment, such as seismic, wind, snow, and temperature. Live loads almost always determine the construction of demountable systems. Seismic loads can occasionally affect design in high seismic regions, such as California, and wind loads, of course, are present on outdoor structures. Temperature loads are caused by expansion or contraction of the system. They may need to be considered in certain exterior installations. What we will first discuss is the difference between uniform loads and concentrated or point loads. This slide shows uniform loads. They're applied on an area basis, usually pounds per square foot, usually across the entire surface, as is shown here. Concentrated loads, conversely, are applied over a discrete area as defined in IBC based on the specific use. The area varies from 2 inches by 2 inches for stairs, presumably to sort of simulate the size of a shoe or a heel, to 2.5 feet by 2.5 feet from most other areas, presumably the area that a person would occupy. Other areas for concentrated loads may be determined from specific equipment component sizes, such as support legs or wheels, which is particularly important for staging components. Now that we have a little background on some of the terminology, let's discuss the requirements prescribed by code. Live loads are prescribed in Table 1607.1 of IBC. You will see that most demountable systems fall into categories 4 or 24 in the ranges from 60 PSF for areas with fixed seating to 150 PSF for stages. That's pretty high. You can see on here that there's nothing that's really higher than that 150, except for an ice skating rink, which of course includes the surcharge for the ice. Note that concentrated loads, while not explicitly defined, may also occur from machinery and other equipment, and should be discussed early in the design process with the demountable contractor to avoid unforeseen costs later in the project life cycle. Note also that concentrated loads should not be converted to uniform loads. For example, as we were talking about for stages, this often becomes the case where we have a lift, a 2,000-pound man lift, for example, should not be divided by the surface area that it occupies and compared to the uniform load rating. Why? Because the concentrated loads on the wheels can cause much more acute local stresses in different failure modes. So you need to evaluate that separately based on the equipment. Here's a table from ICC 300. That is a document used to design bleachers. It's referenced by IBC. You'll see that there's other required loads here. The treads, handrails, and guards are the same as those found in IBC, but you also have lateral or sideways loads. So keep in mind that all structures require a lateral load carrying or bracing system just to remain upright and stable. So even if it's not for a bleacher and the loads are prescribed here, you still have to consider that lateral stability, which we'll get into here momentarily. You can also use the structural building walls to support yourself laterally if you don't have a system such as bracing that does that for you. Let's go into some detail on that. Here's the primary methods of resisting lateral loads in buildings in Figure 1 here. You have shear walls. Those are relatively large vertical elements that support lateral loads via in-plane shear, common in building construction. Simplest example of this is framed wood walls in homes, where the shear is carried by the wall sheathing. In larger commercial buildings, that might be an elevator shaft or a stairwell, where you have a monolithic or a block concrete wall in the middle that takes all of that lateral load. Moment frames and braced frames are more commonly used in demountable equipment design. You saw that in the previous slides with the equipment. The latter being the most common, a braced frame. As we saw in previous slides, most removable equipment utilizes that type of understructure, but you can use a moment frame. That's just a frame that resists bending at the joints. They typically require special, more expensive details, and they're more time-consuming and intricate methods of installation. So usually strategically placed braced frames are used for platform systems. Or again, you can also brace, if it's available, to the structural wall. So if you have a stage or a platform system inside of a building, you attach it to the wall. That wall can usually provide enough lateral resistance that you don't need bracing. But note that for the lateral load to reach these systems in the bracing systems, for example, you need to have a stiff diaphragm. That's shown in figure 2. What that is in a building is usually a stiff floor, a concrete floor on a deck, or something similar to that. You need that diaphragm to be rigid in its own plane. So the analogy is with a platform is the relatively thick plywood or aluminum, and that is attached to a frame which takes that lateral load down through the bracing into the ground. So clearly it's important to take lateral loads into consideration in any case. And as is noted, before planning on creating usable space beneath the removable system, make sure that you have contacted a qualified demountable contractor, check with local jurisdictional requirements to make sure that you can place or design a braced frame to be where you want it. So exterior structures will be subject to wind loads. These loads occur both vertically, uplift, and laterally. Here's an image of a fairly recent collapse. This was in 2011 at the Indiana State Fair. We were not involved with that, luckily, but the collapse occurred as a result of a sudden wind gust, a summer storm. Stage was heavily damaged. 7 people were actually killed and 58 injured. Now, there's lots of failures like this every year with lots of different equipment, but usually it's just property damage, luckily. That's the main consequence. And building code addresses this in a lot of different ways. Of course, the building code requires permanent structures, such as the building you're sitting in, to be designed for a specific wind load. But the requirements for these temporary structures not as clear and vary by jurisdiction. Some jurisdictions require temporary structures to be designed like permanent structures. That's the case in Indiana after this occurred, while others may allow reduced wind loads or require high wind action plans that basically involve a detailed evacuation plan and a team of on-site professionals, i.e. meteorologists using electronics and other systems to closely monitor the current weather conditions during an event. I don't know how successful that is. It seems like it's quite cumbersome. So in the absence of clear code requirements, it's recommended that the design professionals, facility managers, and facility owners utilize a risk management analysis such as we show here. I've highlighted what are, in my opinion, some of the more important considerations. Generally, the team needs to consider the size of the installation and the risk it poses to human life and property damage. In some jurisdictions, the length of time a structure is in use or installed may also dictate the design. Solutions ranging from ballast to soil anchors can be effectively utilized as needed to mitigate these risks, but again, consult your local jurisdictional authority on the issue early in the project. In many cases, this becomes an issue upon final inspection, like the day of an event or the day before. In which case, you really have no time to address the issue if they're saying that you need to have wind load anchorage. So make sure you address that early. Next topic is about how safe a system feels to users and how well it meets its intended function. In engineering, we typically refer to these sorts of issues as serviceability issues. Deflection describes how much a system is displaced or moved under load. Lateral deflection, or sway, is caused by sideways forces, and as we discussed previously, it's usually a lesser concern, but it should be considered at the very least, especially in high seismic regions. Deflection limitations are put in place so that users feel comfortable and adjacent or attached finishes or equipment are not damaged. Most permanent systems, like floors, have very stringent deflection limitations. A floor of of a building, for example, of around L over 360. That's the span over 360. So for a 360-inch span, the allowed deflection is 1 inch. That's so users feel comfortable and excessive movement does not damage furnishings, finishes, or equipment. That's really where that stringent L over 360 really came from, using a lot of plaster walls in early construction in the middle of the 20th century. So these concerns are not as important for most temporary systems. We don't have a finish. We don't have plaster on it. We don't really have a finish. People expect to feel more movement of a temporary system when you compare that to a permanent installation, such as the floor where your computer is. You don't want to see things vibrate or feel that vibration. Deflection is often neglected or overlooked because code does not specifically limit it for the demountable systems, but it's nonetheless important. It should be considered. Design team should think about the use of the system, where it is in the building, and how it might feel to the groups using it. Deflection limitations might be appropriate for demountable equipment in situations where you have large equipment. We talked about various types of lifts being used on the demountable systems, where that's used, you don't want to find inconsistent behavior between the solid floor adjacent to the demountable system, where you might drive a man lift over it and find that it's very soft where you have the demountable equipment. Contact a qualified professional when you're talking about creating a specification for deflection. Too strict a limitation could unnecessarily double or triple material costs. Other important serviceability related issues include dynamic behavior and general durability. Dynamic concerns primarily deal with vibrations of floor systems. We talked about that briefly with the deflection. They're essentially accelerated deflections or movements that occur with occupants and will occur in any system based on the movement of the occupants and the structural properties of the system. More lively activity with more flexible structures may result in user discomfort. Considerations are made so that people will not feel uncomfortable when the system is in use, and there's various acceleration limitations proposed by standards to mitigate that uncomfortable feeling. In many cases, vibration issues may result in structural problems. It's especially of a concern when there's specific rhythmic chant are used. This is a Major League Soccer game. This is from the previous Forkliftable system that we talked about earlier. You have a very specific chant at 2 beats per second that occurs, and if you have a frequency that is also 2, then you will have a problem. You will have a magnification of the forces in the structure. You can't really mitigate those vibrations after the system is installed. It's very costly. You have to add mass to the system. Not practical. So make sure you address that early. The durability of system components can greatly affect the performance as well. Materials that are appropriate for the environment should be selected. Wear surfaces should have appropriate durability for use. Aluminum or stainless is best suited for exterior environments, for example. And walking surfaces should be made of a material that is resistant to scratching, has adequate surface features to prevent slipping. In addition, you should think about the system fastening and operation. If you have fastening devices that are very difficult to use or that may get damaged over multiple uses, you may not want to use those. Demountable system contractors should be consulted regarding system features, setup and strike instructions, things of that nature. Okay, understanding the loading and serviceability considerations is obviously a nice segue into our next topic. Safely engineering structures means that the stress or the load induced in structural elements be below the structural capacity of the element. That's what that engineering looking equation up there in the upper right-hand corner is saying. Simply put, you have to design things so that the stress in them, the force in them is less than the capacity. It should be pretty intuitive. Higher safety factors, as we note here, are used for more sudden failure modes like fracture that could result in catastrophic failure. So for metals bending, it's usually in the range of 1.5 to 2. So design teams should also understand and be able to distinguish between testing and engineered design. They get occasionally confused with one another. Factors of safety are relevant only to engineered design, not testing. In other words, for all demountable systems, including railing, testing involves applying a discrete load to the system in the laboratory or in the field. Per IBC Chapter 17, which deals with testing, it's only suggested or required if the materials and construction are outside the scope of IBC or the standards therein. So testing should not be used as a substitute for engineering is the takeaway. Besides that, the factor of safety, if you will, the load factor they use in IBC is 2.5. That's usually higher than what's used in the material standards, as is explained here, that 1.5 to 2. And more importantly, it can become quite expensive. It's not required for most demountable equipment, but if it's required by the ownership or the GC or the architect, just for peace of mind, should be discussed with the design team and written in the specifications properly. Okay, the loading requirements we previously discussed in the connection to member sizing should be fairly obvious. Larger imposed loads result in larger members to resist them. Material selection is also straightforward. Stronger materials will require smaller sections. Most materials used in demountable design are relatively close in their strength properties, i.e. aluminum and steel. So member sizes are not drastically changed by changing materials. Geometry of the system is the most significant driver in determining member sizing. And I'll tell you why. Materials are often selected so that units can be handled safely by 2 individuals, as we talked about previously. So that drives us to aluminum. It's It's usually the same strength for the tempers we use. It's roughly a third of the weight of steel. Um, However, it's also 3 times as flexible as steel. So that means that for longer spans, usually in the neighborhood of 12 feet or more, you're going to have higher deflections with aluminum. So then it might be more efficient to use steel. The other thing about aluminum is that it requires more specialized labor and processes, including welding. So it may not be as widely available as our manufactured steel components, which means that there's probably a cost component as well. And finally, in exterior conditions, temperature loading that causes expansion and contraction of components should also be considered. Usually, temperature loading can be accommodated with simple expansion joints or with the use of similar materials that expand at the same rates. So that was a brief technical discussion. I hope it's a good overview. And again, I think that the thing I'd like to stress is that it's very important for all members of a design team to have some technical knowledge, and to reiterate that team members on successful projects communicate early and often about these items. So let's go into a few current trends. Newly built sports venues are using larger areas for premium and non-traditional type seating areas, such as suites, loge boxes, multi-use concert spaces, and restaurant or bar terraces. Removable equipment is often incorporated in designs of these areas early in the design process, but in established venues, removable equipment provides the flexibility to transform these areas for other uses. Some other current trends. The Petco, this is actually an example of the trend I just mentioned. Petco Park VIP seating area is an example of retrofitting over traditional row seating. Once the row seating is removed, platforms are built over multiple rows of concrete stadia to create VIP areas. The overbuilt systems can be designed to match the surrounding finishes of the venue, so they have a permanent look and feel, along with the flexibility to be easily removed in the future. It's a popular solution for venues with seating sections that are difficult to sell out. So it's an effort to increase revenue in those areas where they don't typically have people seated. Here's event level seating and party decks. These are also a trendy solution. Same reason, you want to get some people in seats that normally wouldn't be occupied. You provide them a few perks. The event level seating needs to be removable to accommodate different events in the facility. These areas can be built in forkliftable sections with retractable casters to gain maneuverability. And finally, the VIP party decks, they have increased in popularity. You increase the fan experience, add some perks there, and make that into seating where typically you wouldn't have people seated. Another trend in performing arts and multi-purpose facilities, we have a rising or a uplift sort of platform. So this provides an unlimited array of vertical positions within a range of about 12 to 16 inches at the low end to about 48 inches at the high end. You can reconfigure that a little bit. Those are called uplift platforms. Those have become quite popular. So people are looking to do more within an existing space. So there's the rise of esports. That's using venues that are traditionally used for sports, but they're using that now for esports. So you completely reconfigure that arena space. That portable platforming provides venues with the flexibility to adjust seating configurations to accommodate just a huge array of events. We'll talk a little bit about the COVID-19 impact that did transform the issue momentarily, at least. Hopefully it won't bite too much more in the future, but some venues are still concerned with this. There's different areas that you can use, different ways to break up platforming like you see here, where you allow people to be distanced in an exterior environment, of course. Let's look at some specific case studies. We'll put all the pieces together here. I'll take you through a few of the case studies showing demountable equipment applications that illustrate how the components are used and how versatile they are. Some of the technical aspects we discussed and how the project process we discussed can lead to success. So here we have Midtown Arts in Houston, Texas. There's several different ways platforming can be used to add flexibility to a theater, as you can see here. They can be made into an orchestra pit filler or a stage trap in a proscenium style theater. Here for Midtown Arts in Houston, we have a black box theater that has a multi-configurable seating riser. In this drawing, you see the platforms organized in an arena configuration where there's seating on all sides of the performance space. In the picture on the right, you have those same platforms reorganized to make one large riser in an end stage configuration. There are lots of opportunities to customize and make these risers fit the needs of the space, almost an unlimited number of different ways. Zephyr Stadium in New Orleans, we used very similar components, but changed the riser materials to be aluminum to make an ADA infill off of the concourse of this outdoor stadium. This allowed the stadium to add required ADA infill space. It's removable, and at the same time save time and money from using the concrete. We also added the aluminum drink rails that you can see here in the photo. Petco, we already discussed this briefly. 3-tier VIP riser over the existing 7 tiers of concrete stadia. Riser uses weather-resistant platforms and custom guardrail to provide a permanent look and feel, but has the ability to be removed for an event that requires a larger capacity. Jacksonville State University in Jacksonville, Alabama. This is a great example of how we really provided a turnkey solution. Prefabricated, unitized equipment can be utilized to save time and money on the renovation. So here they basically emptied out the arena. We came back and did everything from the floor up, the raker beams, all the steel was designed custom for the arena, and then we put the platforms and the seats on above that. So a turnkey solution, collaboration early in the design phase, and it achieved success both economically and aesthetically. SoFi Stadium in Los Angeles. Exciting project that we completed here recently. It was very, very large stadium, the most expensive at the time. We worked with the architect to come up with a demountable seating solution that would allow them to lay out a wider soccer field for possible World Cup events. The forkliftable seating sections were built to span over suites, and there's also LED scoreboards on them, field pads, glass rail, and a gutter system. So it was almost a building inside the building. Bank of California, we talked about this. This is the demountable system that they can take out for concert events or be used as standing rail for all the rowdy soccer fans when they're having a soccer game. NCAA, for several years we've been working with a partner and the NCAA to convert the seating in football stadiums to be more intimate for Final Four basketball tournaments. Obviously, you have to bring the seating down to the court level. So we basically do an overbuild over the entire lower bowl. We also build the basketball court. That's an elevated stage system for enhanced sightlines. This type of installation requires a lot of design work and collaboration with the execution teams. It occurs on a very tight time deadline, and it's a great example of versatility and usability of unitized components and how the collaboration and communication with our design team leads to success. So please note that there's some sources for technical information provided in this presentation. Here's some of the issues related to demountable equipment, which we talked about already. Code requirement, loading, lateral loads of stability, wind loads, serviceability, safety factors. Again, those are the five main groups. Always contact somebody early to discuss this stuff so you get a project that's within budget and aesthetically pleasing, and everybody's happy at the end of the project. Here's some resources. That concludes our presentation. I hope it was all the information that we shared will help you specify, design demountable systems. You end up with a safe, versatile, and aesthetically pleasing product. Thank you again for your participation, and I hope you enjoyed.